What's up, team? We are here in the physics classroom, and we wanted to show you guys a few cool things. One, we just found this toy. What's its name? Does it have a name?
Spinny disc flyer thing.
Spinny disc flyer thing, and we wanted to show you what it looked like when you shoot spinny disc flyer thing. Give it a rip, Miss Dom.
Do you want it to go up or that way?
That way. Ooh! That was cool science. Let's move over to other cool science. We're going to look at spring-powered roller coasters today. I'm going to try and position this in such a way where you can see the board. I think that works. And we have a roller coaster here that is pulled back. So this is a spring. Its natural length is up here. And the roller coaster pulls it back, so this is a compressed spring. And it's going to be released, and hopefully our roller coaster makes it up to the top of the hill, and we're going to analyze these two positions. And I threw this question out at Miss Dom, what can we ask about this situation? And she came up with some dynamite questions. What could we ask?
So, if you were to launch that roller coaster as is, and then it were to go into a loop-de-loop, would it make it?
Would it make it in a loop-de-loop? What else?
Where does that roller coaster go? What happens to it after it ends right there?
Oh, looks like it falls off the track.
It does.
Womp womp. What else?
What about the velocity?
The velocity. And that's what we're going to explore today. What's the velocity of the coaster? And we're going to do this from an energy perspective. You should be comfortable with the lull diagram, so I'm going to start with the lull and then make this thing more quantitative. So at our initial situation, we've got a compressed spring, and I'm going to call this level my zero height. And the cart's not moving, so there's no kinetic energy, no gravitational energy. All of it is in the spring. My system I'm defining to be the coaster, the earth, and the spring. Notice I have to call my spring part of the system in order to say that there's some spring energy. And my final position will be up here. I am moving this way, so I've got some kinetic energy. The spring now is back to its original state, and it's not touching the cart, so there's no spring energy. I'm some distance, I called 9 meters from my zero line, so there's gravitational potential energy. And I'm going to say that this track right now, we're going to presume it to be frictionless, so there's no change in internal energy. Now the mathematical expression to start to solve for the velocity of the roller coaster would look something like this. There's no work acting on my system, so I can say initial energy will be final energy. The only initial energy I have is the spring, and I'll say that that's USI, I for initial. That equals my kinetic energy final plus my gravitational energy final. My expressions for these types of energies follow. 1/2 kx squared equals 1/2 mv final squared plus mgh. H being the distance from here to there. Now it's a matter of just plugging and chugging. I know all of these variables except for VF, so I can whittle this down and get a VF of 13.7 meters per second. So if our assumptions hold true, we should see the roller coaster going at 13.7 meters per second. I forgot to mention all of this data over here, but hopefully you saw it and you were able to solve the problem. The mass of the roller coaster is 3,500 kilograms. K, remember this K is the spring constant. This is how stiff the spring is. And in order to get this roller coaster moving at a large velocity, because it weighs so much, you need to have a very large K value. And delta X, this is the compression of the spring. So the spring at rest is out here. We've compressed it 8 meters. So you can solve for the potential in the spring. Now let's suppose that we actually do this, like we see this situation and we use a radar gun to measure the velocity of the roller coaster at the very top, and we don't see 13.7 meters per second as the velocity of the roller coaster. Did we violate the laws of physics? Well, not really. So we've measured a velocity of the coaster to be 10 meters per second. We need to check our assumptions. We go back to our lull diagram, and we have the same initial setting, but now I'm going to consider the track as an external influencer on my system. There's some friction acting from the track to the coaster. So my final point ends, it looks a little bit different. Now I don't have 2 bars of kinetic energy. I have the same amount of gravitational energy because I reach the same height, but now some of my energy goes towards raising the internal temperature. So the track is heated, the roller coaster is heated, so there's some energy lost due to raising the internal energy. And we could solve this using a mathematical expression where we set the initial energy equal to the final energy. So my potential in a spring is equal to the kinetic final plus the gravitational potential energy final plus the change in internal energy. If I rearrange this, I could throw these 2 terms onto the left side. I know that's a very loose term, but subtract the 2, and we get an expression that looks like this. Potential energy of a spring minus kinetic energy at the top minus the gravitational energy at the top is our change in internal energy. We could take it a step further and solve for, say, the force of friction. So our work due to friction is what is raising the internal energy. So I know my work due to friction because I just solved for the internal energy change. And I would just need to know the total distance that the roller coaster is traveling along the track. So if I was given some information about how long this section is and how long the total length of the coaster is to get up to that final point, then I could solve for the force of friction, assuming that it's constant. And that's the algebra that follows. Hope this made sense. Hope you learned something about roller coasters, about flying wingy dingies things. All right, see ya.